Hi everyone, welcome to this next introductory video to walk through some functionality from the mvgam R package. So this video is going to build a little bit on what we went over in the last video, which was just an introduction to the package and some of the things you can do in mvgam, how to actually work with mvgam objects to create plots and do other kinds of analyses after you've fitted your models. Now we're going to talk through some of the main functions of mvgam, some of the main things that you might be interested in doing when it comes to time series modeling. So the purpose of this video is to talk through hierarchical GAMs. So these are a really useful class of models that we can use for fitting time series models when we've got more than one time series and we want to try and learn from those time series jointly. We want to learn some kind of effects at the same time from more than one time series. In particular, we're going to talk about trying to learn nonlinear temporal trends from more than one series, where the trend estimate for each series is informed by the trend estimate for all the other series in the data set. So this is a really useful thing to be able to do that's actually very challenging to do with existing kind of time series and forecasting software. So hopefully you find that useful. It won't be as big of a video as we went through in the last one. So the purpose of these is just to give you some bite-sized chunks of ideas that you might want to try and tackle with mvgam and time series modeling. So I'm just going to start by loading some of the libraries that we'll need. We're using mvgam, of course, as well as some tidyverse functionality for data manipulation. Most of the plotting will be done with ggplot, and I'll use marginaleffects and gratia for interrogating and understanding the models that we're going to fit. And I always like to set a ggplot theme to keep my plots consistent. Okay, so we're going to work with a data set that's available in the Mars R package, which is a really useful package for fitting state space time series models. And this is a data set of American kestrel abundance. It's actually abundance that's been sort of corrected for some detectability and other things that have been used to try and adjust this abundance measure. So it's not actually in counts, but it's basically a time series of relative abundances of American kestrel in some different regions in Canada. Okay, so the data is available in the Mars package, and we can load it directly into R if you've got internet access by just loading it from a URL. Okay, what we get out of this is a matrix. You can see it's got 40 rows and 4 columns. The first column is just the year. So this was collected on an annual basis in these 3 different regions and in British Columbia and Canada. Okay, and the purpose of this data set is to try and understand, are there relationships among the trends for each of these, for the abundance of the species in each of these regions. Now, because this is in a matrix, this isn't the right form that we want for mvgam modeling or for any kind of regression modeling in R. We'd prefer to have a long format where we have one column that identifies the region that we're talking about, and then we have the year in another column, and then we'd have the actual adjusted count in another column. So that's long, so we stack those on top of each other. And so I've just got a little operation here to do that. I'm going to loop over each of the regions using lapply, and then I'm just going to create a data frame for each region. And I'm going to exponentiate those adjusted counts. So in the Mars package, so that package, everything has to be able to be modeled using a Gaussian observation family for the Mars package, which is useful because it makes the operations really fast, but it's a bit restrictive because you can't really handle count data or non-Gaussian data. But we can handle those kind of data in mvgam, so we're going to actually reverse that logging. The logging was done. If we read through the details of the Mars package, you can see that they used a log of x+1 or something like that. And so we're just going to undo that. So I'll just define the regions and then loop over those and create my data frames. And then I bind each of those data frames together. And then I'm just using dplyr to do a few other things. I'm adding, actually don't need that for this example, but a factor of the year. I'm adding factor indicators for the region and for the series. as well. So this gives us the kind of data that we want in mvgam that looks kind of like this. We've got year on its own variable, and then we've got a separate line for each region's estimate in each year. Okay, and we can obviously look at the structure of the data. All of this is just standard sort of data exploration things, and you might prefer to do this in a different way, and that's fine. Doesn't really matter for our purposes. But we can see that what we've got here is our series indicator, which is what we need for mvgam to define the different time series. It's just the names of those regions. Okay, and we're going to get into some models pretty quickly in this example because all the other exploration stuff has been gone over in the previous video. So I'm going to use some forecasting evaluations in this set of examples. So I'm going to split the data for cross-validation, where all the years up to and including 2001 I'll be using for training, and then all the years after 2001 I'll be using for testing. Okay, and that gives us seven holdout time points for each time series. Always useful to plot the series. Now that we've got it in the long format, we can easily plot the series using plot mvgam series, and we just say what the actual outcome variable is for this this particular set of data, and we'll say at first we want to plot all the time series together, and that's what we get here. Okay, and you can see we've got some general patterns of kind of sort of smooth change where each series tended to go up a little bit back in the 80s and then declined a little bit after that, but the levels of those, or the magnitudes of those changes vary for each series. We can see clearly we've got non-negative data here, and these are real values. They're not integers, so we'll have to handle that in our model. But really, this is a useful set of data to try and test hierarchical GAMs, because we might expect that, because each of these regions is kind of a neighboring region, and we're talking about the same species, that the actual temporal trends might be somewhat related among each of those regions. And we can actually try and fit a model that will allow us to do that. Of course, we can plot features of each series one at a time, like we did last time in the last example. So I'm just looking at the first series here, just saying series equals 1. And again, here we can see the time series itself, the training and the test data, because I fed the test data there to new data. And we can see features of this plot. I can zoom in on that so you can see that a bit better. We can see the autocorrelation function, we can see the cumulative distribution function, etc., and the histogram, and all that's going to give us ideas about what kind of model we might want to fit. Okay, I can do the same for the second series, which shows a little bit more autocorrelation and more of a sort of more evident kind of peak that might have happened back in the early 80s as well. And same for the third series. And hierarchical GAMs, they really benefit from when you have quite a lot of series. 3 is kind of a minimum, but the more you have, maybe the more opportunity there is for learning from each of those series. Okay, the outcome variable looks like this. If we look at those adjusted counts for all the series kind of aggregated together, and you can see we've got a heavy kind of tail here to the right, so a bit of skew in this. Again, these are non-negative values, they're real values, so maybe a gamma distribution might be appropriate for modeling these data. You could also try a log normal or a Tweedy, for example, but a gamma should be fine for this one. And again, I'm calling the summary, and that gives us an idea of what the bounds are of this adjusted count. Okay, so we're going to just jump straight into a model here. So what we're going to do is try and fit some kind of hierarchical GAM to these data. I'll give you a reference at the end of this video, and I'll put some references in the notes below for you to have a look at hierarchical GAMs. There's some nice papers that kind of go through these in a bit more detail. But a hierarchical GAM is just a simple model where all we try and do is fit some shared nonlinear effect that's shared between all the groups, in this case, all the series. And then we fit some other nonlinear effects that allow the overall effect for each level of that group to deviate from the shared effect. That's basically what we mean. We're sort of fitting an additive model where we have particular decomposition of some nonlinear effect that allows for sharing of information across the levels of those groups. If you're interested, you can look at There's a help page on GAM models from the MGCV package, which is what's used to set up the splines for all the effects in mvgam, give you an idea about how you set up splines and some of the key things you can do. You can also have a look at there's a help page on mvgam formulae, how you set up formula objects in mvgam. And then you can look at how to define priors. Because mvgam is a Bayesian package, it fits Bayesian state space models using Stan as the back end. You can set priors on key parameters. But I went through all that in the last video, so I'm not going to dwell too much on that here. But basically, the model that we want to fit is going to be a state space model, where we're just going to give a different intercept to each series in the observation model. And that will allow us to have latent states that are kind of zero-centered. And we can control how those states evolve by putting terms in the trend formula. So that's the actual latent process model. Okay, so in each latent process model, these are going to have, they don't have any intercept because we don't need that once we've got the intercept in the observation model. But what we're going to put in there is our hierarchical gamma effect. We're going to have a shared trend, a shared smooth effect of year that's shared by all the series. And then each series is going to have a deviation smooth. Okay, the way we set that up, there are various ways of doing that in MGCV. And again, that reference from Peterson et al., which I'll put in the show notes, is probably the canonical reference to understand the different ways you could do this. But basically what we're doing is saying each series, they're going to share that smooth of year, and then each series is going to have its own separate smooth of year that it can deviate from that shared smooth of year. The key to doing this in a state space model in mvgam is that instead of putting series here, we put trend. Okay, so trend is a way of IDing each series in the actual latent process model. It's a little complicated about why that is, but basically that allows us to have fewer latent processes than we have observation series if we wanted to do that. We're not going to do that in this example. So each series has its own latent process model, but you could actually do that if you want dimension reduction. But we're going to use this SZ basis. And this is a really useful basis. If I have a look at this help page on factor smooth interactions from MGCV, you might not be able to read that on the screen, but this is a sum to zero smooth interaction where we have those separate smooths of year for each series, but at each point along that smooth, the overall effects have to sum to zero. So it's a really useful way for ensuring identifiability and ensuring that each of these actually does have to deviate around some central shared smooth of year. So this central one will act as a kind of population average temporal trend, which can be nonlinear. And then these effects here are going to allow each series temporal trend to deviate from that shared one. And we're going to use a gamma observation model for this model. Okay, so often it's again valuable to feed your formula objects and your data to get mvgam priors, to have a look at what the default priors are for that model. You can view that. Again, you might not be able to see that on the screen, but you can see what parameters you can actually set priors on and what the default priors are in Stan language. Again, won't go into too much detail about those here, but you can read about how to change those. mvgam uses the prior function from brms to be able to set priors. There are various ways you can do that. But we're going to set priors in this model when we feed it to mvgam by just setting a standard normal prior for those intercepts. So there's a shortcut in mvgam that allows you to do that for any fixed effect. You can just say class equals B, and we're going to say a standard normal prior for all fixed effects. Okay, and the reason we want to do that is because in mvgam, the gamma distribution is parameterized using a log link function, just like in brms. And on the log scale, you know, a standard normal, which is a normal 0, 1, is appropriate for these kind of fixed effects. Okay, so that's how we're going to fit this model. We're going to feed this formula, our hierarchical GAM for the latent process model, and then we're going to set priors just on those fixed effects, those intercepts. We feed in the data, so the training data and the test data. So we'll get automatic forecasts for the test data from the model. We're also going to simplify this model a little bit by forcing each series to share the same gamma shape parameter. So by default, if you have more than one series and you have an observation family like a gamma or a Gaussian or a negative binomial that has its own sort of separate parameter, then each series is going to get a separate estimate of those. But you can force them to share those parameters, which might make sense in this case. We might not have enough data to estimate separate shape parameters for each series. And finally, we're going to non-center those latent states. I went into this a little bit in the last video, but this is just a trick, computational trick that often speeds up state space models. And I'll use command stand for the back end here. Okay, so again, same as last time. When you call this model, it has to compile the model file down to from Stan language to C++. And then after that compilation, the fitting is reasonably fast. So again, usually you might spend more time waiting for compilation than you actually wait for the model to fit in mvgam, same as you would in brms. Depends on the complexity of the model too. Okay, so we're waiting for that compilation to happen, and then we'll start seeing some progress here in a moment. This is 3 time series. You can see our training data has 99 observations total, so there's 33 time points for each series. It's not a big data set, and this is not a complicated model, just 2 nonlinear effects in there, 2 penalized spline effects. So it won't take very long to run. You can see it's flying through now, and the execution time is 3 seconds. Okay, once that's finished, again, you can have a look at what methods are available for objects of this class, which is class mvgam. We've got lots of methods available. You can learn how to understand that model. You can look at the Stan code. Again, I won't go through this for this video, but you're welcome to do that. And you can also call how to cite for this model to get an idea, a brief idea of what you could actually write if you wanted to start writing a methods section for these models. It'll give you appropriate references there. And this will update depending on what's in your model. Okay. All right, for the model, again, if we call summary, we're going to get summaries of lots of things in here, lots of basis coefficients. And we might not want to look at all of those, and we'll get sort of approximate significance of the smooth effects. Again, we can exclude a lot of those beta coefficients if we're not really interested in looking at each of them on their own and just look at the overall terms themselves in the model. And you can see that it's converged nicely here. We're not getting any warnings or anything from the sampler. Again, main diagnostics, look at the R-hats, the split R-hat diagnostic, make sure that most of them are quite low. They're all far below 1.1, so we're happy on all of those. That's for all the parameters in the model. We can have a look at trace plots of the shape parameter, for example, which tends to be a little hard to identify in gamma regressions, and the estimated sigmas. So again, because this is a state space model, there's a latent process error parameter, one for each series. Okay. And this shape parameter kind of acts as our observation error in a gamma model. So we're getting estimates of both of those. Everything's fine, everything's converging well, but we want to really look at understanding these models. So we can use the Gratia package to draw the component smooths. And here we've got that shared smooth. I used a cubic regression basis to make things nice and fast, but also because these tend to be a bit wigglier, so you can sort of see how they kind of wiggle around. And then we can see those sum to 0 smooths for each series, which is how they deviate from that shared smooth. That's really valuable if you want to look at each smooth effect kind of separately. Gratia is probably certainly the easiest way to do that. But you can also look at them kind of together using conditional effects, which is a function from the mvgam package, which will plot all your conditional effects one by one. And what that does is give a series of plots. First, it plots the intercepts, and you can see we've got our estimates for the intercepts. This is on the outcome scale. And we've got the actual shared smooth on the outcome scale, which looks a bit like that. And then we've got the deviation, the overall smooth, sorry, for each series. So this is the shared smooth and the deviations put together. So this is each series kind of estimate a nonlinear shape, and you can see they're kind of related, but they're also a little bit different from one another. And the hierarchical GAM has allowed us to learn that. It learns how much should they be sort of pooled together to this shared effect, and how much should they deviate from one another. Again, we could change type to link and plot all those on the link scale, and they'll look a little bit smoother there, because that's not taking into account the gamma observation model. Okay, other things you can do, it's really valuable to use marginal effects to calculate all kinds of predictions and contrasts and other things from these models. Just about everything you can do in marginal effects should work in mvgam. So one thing you could do is plot the kind of average prediction on the outcome scale for each series. What's the kind of average adjusted count with some uncertainty estimates? And you can see what those are for each series, and other things that you can do. And we'll go into some other plots later. When we've got multiple series, it's often useful to use some posterior predictive checks that are kind of grouped by series. For example, if we call PP check, we can look at the cumulative distribution function for each series. You know, how well did the predictions fit the observed data for each series? Okay, and looking for deviations there can give us an idea of, you know, are we under predicting or over predicting for any series in particular. We don't see too many problems there. We can also do that as a density plot if you're more familiar with looking at those. Okay, and so each of those are going to plot posterior draws from the model as y rep in the pink, and then the actual observed data in the dark red. And it's just useful to look for differences among those or deviations among the predictions. And you can read more about posterior predictive checks and some other references. Okay, we can also look at the hindcasts from this model. And when we call the hindcast function, we get the hindcasts for each series, which we can plot together like this. And you can see that we're getting pretty good fits to the observed data. These are posterior hindcast predictions for each series, plotted against the actual observed data. Okay, and that fit the data really nicely. And that's before we can plot residuals, which are randomized quantile residuals for each series. And we don't see too many patterns there, a little bit of patterns there, and the residuals are fitted, but that's quite common for gamma distribution models. What we really are looking for is there any autocorrelation that we're not capturing here? And we don't tend to see much, maybe a little bit for that third series there. But because we've already computed forecasts by feeding new data to the model, we can just extract those using the forecast function and plot those as well. And this will plot the hindcast together with the forecasts. Okay, and here you can see what the forecasts look like. So when we fit splines, they tend to extrapolate linearly. So they're extrapolating kind of linearly based on whatever the last estimate of the slope was towards the end of the training data. And you can see that extrapolation is probably not appropriate for most of these time series. The forecasts tend to miss quite badly. And so we might want to update this model with something a little bit more appropriate. Okay, we can also use plot predictions for marginal effects to plot those using ggplot, using something like this. So I'm just feeding the faceting by year and series here, and plotting the actual predictions using marginal effects. It shows basically the same information, you know, fitting the observed data quite nicely, but then the predictions maybe don't look so realistic. Okay, but there are many other things you can do with these models, and I'll go into those when we fit a second model. But everything I do in that second model can apply to this one, and it's useful to have a look at that hierarchical GAMS reference from Peterson et al. And a few others that I'll mention as well, to understand the things that you can do. I mean, we could try and ask, you know, what were the slopes of each of these temporal trends for each series? You know, when were they growing the fastest or declining the fastest? When did they peak? We can compute differences among each of the series. We can compute an average temporal trend. So all those things that we can do with these models that can be really valuable to help you understand a bit more about what the model thinks has happened in your time series and how the model is actually learning from all those time series at once. And those kind of investigations become really critical, especially when you're working with lots of time series, Not only is the model learning from all those time series at once to estimate those shared effects and those deviation effects, but you can actually ask the model more interesting questions about those that level of sharing. But before I go into those, I'm actually going to fit a second model. It's going to show a little bit more about what mvgam can do, and we're going to replace those spline effects with Gaussian process effects from BRMS. Okay, in Gaussian processes, they will give you nonlinear shapes, nonlinear functions. They might look similar to a spline, but they tend to behave much better when it comes to interpolation and extrapolation, and they can often be a lot more interpretable as well. So what we're going to do, again, I'll give you some links so you can look at the help page for GP. That's what we're going to use from the BRMS package. And this allows you to set up Gaussian processes. And they can be set up in a very similar way to those splines that we set up before. In particular, what I'm going to do is fit a GP of year, a shared GP of year. And I'm going to use the K argument here, similar to what I did before. These can be set generally a bit higher because they give you better estimates of the length scale of the GP. But you can read about details of those later. It's not that important for this video. But same thing as before. We have a shared GP of year, and then we have deviation GPs of year. So each trend or each series in the process model gets a separate GP of year. And so by adding these two terms together, we get the overall effect for the overall temporal trend for each time series. I'm also going to add a little more complexity by adding a correlated AR1 model for the errors in the process model, just to mop up any remaining autocorrelation. This can often be valuable if you want to estimate a nonlinear trend in a time series, but you also need to capture any short-term temporal autocorrelation. Okay, very difficult to do that in other packages in R. Especially if you want to actually estimate those AR parameters, but very easy to do in mvgam. You just need to think a little bit about priors in some cases. Okay, so I'm not going to bother looking at priors here. I'll show you the priors down below, but basically we're going to fit this model, and I'm going to set the covariance kernel for these GP effects. If you're using the latest version of BRMS, then you'll actually be able to change these covariance kernels. This version's only currently, as of now, as of February 2025, it's only available on GitHub, but it'll be available on CRAN soon. But this version allows you to change that. So in previous versions, only the quadratic exponentiated kernel could be used for GPs, but now you can change it. You can fit Matern kernels and exponential kernels and other things. Exponential tends to be simpler, so it fits a lot faster. And so I'm going to use that in this case. And I'm going to be specific with priors in this case. So when we're fitting an AR1 process as well as nonlinear trends, we often have to choose which one of those do we want to be more flexible. And so I'm going to have a restrictive prior on the process error, those sigma parameters that we looked at before, to make sure that this AR1 term can't move around too much from time point to time point, because I want most of the variation to be captured by the GPs. And then I'm going to set priors for the actual alpha parameters of the GPs, again, controlling how much they can move around. Okay, I won't go into details again about why I'm doing this, but just know that it's often valuable to set priors on some of these things. And the more you look at the model and fit different models and understand those parameters, the more you start to get a handle on how they're working together. Okay, same as before, we have a standard normal prior for the fixed effects, but I'm also setting a kind of informative prior for those AR1 terms, because I expect there to be positive temporal autocorrelation in this, in that latent process model. Everything else is the same as before, except now I'm showing another functionality of mvgam that I can change the adapt delta parameter for MCMC sampling in STAN. Basically, if you set this to be a bit higher, it will sample a little bit slower, but you'll get more precise estimates. And this is because when we want to fit, again, nonlinear trends as well as AR parameters in the same model, often that can lead to some non-identifiabilities, and we might want the sampler to go a bit slower and to be more precise. Okay, so I'm going to get this one compiling as well. This one will take a little bit longer because it's a much more complex model, but hopefully it's showcasing some of the things that you might be interested in doing for your own more advanced time series modeling exercises, where you might want to capture nonlinear trends. You might want to share some of that nonlinear trend information across multiple time series, but you also might want to capture autocorrelation. And by setting core equals true in this AR call for the trend model, we're going to allow those process errors to be correlated among the series, which again makes a lot of sense. You know, this is the same species in kind of neighboring regions, and we expect if we get a higher than average count in 1 year for one region, we might get higher than average counts in neighboring regions in that same year, and that's what that model is going to allow us to try and capture. Again, you can't really do this, as far as I'm aware of, in any other software in R, at least not any of the sort of bigger packages like brms or mgcv or other time series modeling packages. So it's just highlighting a little bit of some of the more complex things you can do in mvgam. Okay, we'll wait for that to compile. Again, compilation will be a little bit slower here just because of the stand model itself. It's just bigger. It just has more lines in it. But you can see, again, it's moving pretty quickly here. The default in mvgam is 500 warm-up and 500 sampling iterations. And again, that for 4 parallel chains. And that's often more than enough. So the whole thing finishes in 18 seconds on my computer. And again, you can look at stand code and you can look at how to cite this model. I'll leave that to you if you want to have a look at that. But actually, the how to cite is quite useful in this case because it'll give you a reference for the GP effects that you can look at, these Gaussian process functional effects, because this uses an approximation of GPs, which is one of the reasons it's so fast. And then you'll get an appropriate reference for that. Again, calling summary, we can see we've got only a few parameters for the R-hats aren't quite as low as we'd like. That tends to be, again, non-identifiabilities between latent process error and observation error, the shape parameter. That's going to happen in a lot of models where you fit state space models, and so often we could put a different prior on that shape parameter to try and help that, but it's not that big of a worry in this case. Again, diagnostics will look pretty good, except for those few R-hats that are a little bit higher than we'd like. And we can look at trace plots again for all of these parameters. You can feed in whatever variables you want into the MCMC plot function. And by setting regex equals true, we can just pull out plots for each of those. And they're all looking pretty good except for that shape parameter again, which is hard to identify in these models. Okay, all the posterior predictive checks will work the same for this model. They'll all tend to look quite good. They're going to fit the observed data quite nicely. This one might fit a little bit better because it's more flexible than the previous model. But the things we want to really get into is actually plotting those temporal trends. Those are the things we're interested in the most in this model. We want to know what are those nonlinear shapes, and plot predictions will give that to us directly. And again, it's different to Gratia. If we call Gratia draw mod 2, trend effects equals true, we can plot those GP effects. But this doesn't really tell the whole story because it doesn't tell how each of those effects add up to give the overall shape. And so we'd rather actually plot them using marginal effects to actually plot how they add up together. And again, I'm shortening the confidence level here just to make these easier. So if we go by the default 0.95, it's just a little bit harder to differentiate amongst them. So we can change that in marginal effects, just to make them easier to differentiate. And here we can see that the BC, British Columbia region showed quite an obvious peak and at some decline. The others kind of moseyed along a little bit more over time. Maybe the Saskatchewan one showed a little bit more of a later peak, but we can actually test that later on, and I'll show you how to do that. But that's really valuable. And again, the more series we have, the more valuable these kind of plots become. become and the more valuable these models become. We can also plot that on the outcome scale by including the actual points, and we can see these are the actual, what the model would predict for this actual time period for these series. Okay, something else we're interested in here is that AR1 term in the model, so that correlated process error with autoregressive residuals, especially in the actual variance-covariance matrix for those process errors. So we can pull those out using the sigma. So sigma is the name of those parameters. And what I'm doing here is actually rearranging those. I'm just saying I want a matrix of sigma parameters that I'm calling sigma pars. And I'm just saying the names, where I want them to go in my matrix. And the reason I'm doing that is because by default, when you pull out parameters from matrices that are estimated in Stan, they'll be transposed. They'll be in the wrong kind of direction. So I'm just making sure that those go in the right direction when I plot. Okay, so I'm feeding it these names for these sigma parameters in the right direction. So when I pull those out, you can see that my plot is in the right direction here for this estimate of the variance-covariance matrix. So I've got my rows going down this way and columns this way. Okay, so this is really valuable if you're interested in multivariate modeling, multivariate time series modeling. We can see we've got a lot of evidence for positively correlated process errors between the first two series here, and maybe a little bit of evidence between series 3 and 2. Most of those estimates tend to be a little bit positive, but certainly strongly positive for series 1 and 2 or positive correlated process errors. Okay, and you can do lots of things with that. Now you can compare these models using Liu compare. I caution against that in a lot of cases because these flexible state space models, they have a lot of parameters in them because each latent state estimate is a parameter in the model. So it's a bit hard to actually get an effective and accurate estimate of this leave one out cross-validation prediction-based performance. So we can compare these models, and the models, they tend to suggest that that second model fits better than the first model. It has a higher log predictive density, but I would still take those with a bit of caution. All that's doing is comparing based on the in-sample data. So something that might be more valuable is to actually compare the forecasts from each of these models. So what I'll do is pull out the forecast from each model using the forecast function, and then I'm going to operate in a loop, actually plot the forecast for each series from each of those models. And this will also give me a calculation of the continuous rank probability score, which is a proper scoring rule for these forecasts. So I'll get an estimate of how well each forecast performed for each model on each series. So again, I'll operate across each one, and you can see what's printed out on my console here. For series 1, the spline model gave me a CRPS about 1.8, and the GP model gave a CRPS of about 2.6. So that spline model did better for the first time series. But for each of the other time series, the GP model did much, much better. It had a far lower CRPS. CRPS is something we want to minimize as a proper scoring rule. And we also get plots for each of these. So if we look back at the first series, you can see what the forecasts look like for each model. And we can see why the spline model did a bit better. Remember, it's assuming that everything's going to decline linearly through time. And there was a slight decline in the actual observations for the next few years. So the model got it right for that time series, whereas the GP tends to forecast a little bit more flatly for that series. So it missed that decline. But for the other series, the spline again expected a strong kind of linear decline, and that tended to be a very bad assumption for the next two time series. So the GP with the AR dynamics tended to give better forecasts, better uncertainties for those next two time series, particularly for that third one. Again, you could calculate other kinds of scores. You could calculate, a multivariate score to score all three time series at once. I'm not going to do that in this example, but you could look at that in the previous video to see how you could do that. But in all cases, we're going to find that this GP model does better, and that's not that uncommon. GPs, as I said, tend to extrapolate better than splines do. They'll extrapolate a little more kind of non-linearly using the covariance function that they've learned from the entire history of the time series, whereas splines will just extrapolate linearly. But I've mentioned a few times that we can do other interesting and useful things with these hierarchical kind of nonlinear models. The same applies for whether we do that with splines or with GPs. And in this case, we're going to use the GP model, that second model, to look at some other things that we can do. For example, we could actually ask, what is the rate of change for this temporal trend, and what's the shared temporal trend across all the regions? So we could average across that temporal trend for each time series to give us an overall shared trend. And then we could take that overall shared trend and say, well, when was it growing and when was it declining in time? And that's really valuable if we consider maybe all of these regions are one large population for this American kestrel species. We want an overall shape, an overall trend for all those populations together. And you can use marginal effects to do all of this, right? So what I'm going to do is define a sequence of years between my minimum training year and my maximum training year. Okay, and because year is numeric, it's just going to give me kind of decimals of year, which I'm going to predict over from my model. So I'm going to take this sequence of years and I'm going to generate a prediction on the length scale for each time series in my data. And that's what I'm doing here. I'm feeding a data grid from marginal effects saying I want this year sequence and I want every level of the variable series in my new data, and I'm going to predict from that. And then what we're going to do is aggregate by year. At each point in this year sequence, we're going to take the average effect. And that's going to give us an average overall nonlinear temporal trend on the length scale. This tends to work better on the length scale because it doesn't take into account this kind of extra noise from the gamma observation model. So I'm going to make that plot first. And then what I'm going to do is using wrap plots from Patchwork, I'm going to add a second plot that's going to do the same thing. It's going to give me predictions for each series during that year sequence. But in this time, we're going to use plot slopes, and we're going to actually calculate the first derivative of that temporal trend. What was it growing or was it declining at each point in time? Again, on the length scale. Okay, and I'm going to put both of those together with wrap plots. So I'm going to call this, and this will take a little while because it's generating a fairly complex grid of values to predict over. So there's quite a lot of prediction happening here. But when we plot these two together and we add some nice labels to it, we get something like this. So here's that shared temporal trend, again, on the length scale for all the series kind of averaged. And we can see that overall it tended to peak, sometime in the early 1980s. But we can also get an estimate of that first derivative. Any estimate that's above this zero line suggests the trend was growing. So the population was growing during that time period. And then when it dips below that zero line, that's when the population is starting to decline. And we get uncertainty estimates for each of those. And that's really valuable. You could look at each point in time on a fine enough grid to sort of say, how quickly was it growing? When was the peak? All these kind of things. And that's really valuable for time series modeling. Other things we can do is use plot comparisons from marginal effects. So we can actually make comparisons among those temporal trends for each series. So I could actually, again, use that same new data grid, generate predictions across all those time points for each series. But now I'm going to take a pairwise comparison between those estimates for each series. And I'm going to plot that, again, using marginal effects. And that's very valuable if you want to calculate something called difference smooths, if we're talking with GAMs. But that's kind of the same thing with GPs, is sort of what's the difference among each of those trends at each of those time points, again, with appropriate uncertainty estimates, which we'll kind of get for free from marginal effects. And because I said to do a pairwise comparison for each of those variables, we get every possible pairwise comparison. So again, British Columbia minus Alberta, for example, and it tends to be positive because British Columbia was larger across just about every time point. in its sort of temporal effect. And likewise, we can do the same for the other pairwise comparisons here. And again, that's really valuable to understand, when were these trends growing faster than the other trends, for example, or when were they deviating, etc. So lots of interesting questions you could ask there. And you can see, again, I use series equals pairwise when plotting that. And finally, I'd like to go through some other things that you can do, more focused questions around the actual the growth of these things. So we could ask, well, when in time did they actually reach their peak growth? When was each series trend growing the fastest? So you can set custom functions in the comparisons function in marginal effects. So I'm defining a function that says, at each pair of points, it's going to calculate the slope using a sort of finite approximation, and then it's going to say when was the maximum slope for each time series. Again, you can read more in the marginal effects documentation about how to do this and other things you can do. But by creating this custom function and again plotting over that same data grid, I'm going to say, give me this comparison, the max growth comparison for each time series. When was the slope growing the fastest? And it's going to tell me actually when in that variable, in the year variable, was it growing the fastest, and do this for each series. Okay, so what this is going to do, I didn't define my function. What this is going to do, operate over that grid and using a finite approximation, say when was it growing the fastest? And you can see we get a lot of uncertainty in our estimates for Alberta and Saskatchewan because they had different periods where they were kind of growing and declining. But we have a fairly confident estimate for British Columbia because it sort of peaked and it was accelerating the fastest toward that peak in kind of like 1977, 78, something like that. Okay, so that's really valuable. We can do those kind of things. And if we have a look again at the actual trends, we can see why that's the case. Again, these other series, they sort of grew a little bit and declined a little bit. There wasn't an obvious period where they were growing the fastest, but there is an obvious period of fast growth here in sort of the late 70s for British Columbia. Finally, we can do something similar. We can define that function directly in comparisons. And in this case, we're not going to say when was it growing the fastest. We're going to say what was the fastest growth rate for each series. And then we can compare those growth rates for each series using the hypothesis argument. We're going to say, give me a pairwise comparison of the maximum growth rates for each series temporal trend using the comparisons function. And that's just going to give us a printout of what that actual comparison is. And we can see here again, British Columbia minus Saskatchewan, it tends to be much larger, its maximum growth rate compared to the maximum growth rate for Saskatchewan. And again, Alberta minus British Columbia tends to be quite negative, which again suggests the maximum growth rate for British Columbia was much larger than the maximum growth rate for Alberta. Again, so I'm sure you can imagine many other kinds of questions and comparisons you might want to make. And you can actually do hypothesis tests with, approximate or p-values for a lot of these tests using marginal effects. So many questions you can tackle. Okay, so that was a short but hopefully useful video on hierarchical effects in mvgam and give you some idea how you can learn from more than one time series to make all sorts of inferences, as well as give good and useful forecasts and predictions. So please stay tuned for the next video where we'll go into some more specific multivariate time series modeling techniques in mvgam. And thank you for listening. I appreciate your comments and your attention.